to good measurement and valuation modeling approaches in the planning process and getting to good design and control schemes in the operational processes to tap into that load flexibility and meet customers at a point where they value providing that to utilities and to the grid. So we're going to dive into that with a great couple of panelists today. We're going to go a little bit out of order from your agenda, and we're going to start first with Andy Satchwell. Andy's a research scientist and deputy leader in the Electricity Markets and Policy Department at Lawrence Berkeley National Laboratory, where he leads and conducts research on financial analysis of electric utility regulatory and business models, demand flexibility, energy efficiency, and electric system planning. He also co-leads research on building sector decarbonization pathways, with a particular focus on the electricity system cost impacts of building efficiency, flexibility, and electrification. And he's authored dozens of publications, and his work has been featured in several major news outlets, including Forbes, San Francisco Chronicle, and NPR. So Andy's going to be talking to us here on valuing the value of building load flexibility. Go ahead, Andy.
Great, thanks Obadiah, and thanks to the organizers for giving me this opportunity to share some exciting research with you. So I'm going to be talking with you today about a national roadmap for grid interactive efficient buildings. This is a Department of Energy, Office of Energy Efficiency and Renewable Energy roadmap that's intended to describe both the potential and opportunity for flexible buildings as a grid resource, and then to talk about both the barriers, but more importantly, recommendations to overcome the challenges to achieve wide-scale and widespread deployment. The roadmap is available at the URL here, the gebroadmap.lbl.gov, if you want to follow up and get into more of the nitty-gritty. So why grid interactive efficient buildings, or GABS, as the new hot acronym for the industry? So why GABS? Well, in part, and I think this sounds like a particular focus and interest for the ESIG members, is to integrate the growing share of variable renewable energy by using flexible buildings as a grid resource. It can also result in benefits to the utility and to customers by reducing the cost to replacing our aging infrastructure and improving the system reliability and service. Importantly, it's a tool in achieving decarbonization goals by reducing fossil fuel generation and increasing heating electrification at the customer site. And then from the customer perspective, there's been an interest in an increased deployment in energy technologies in the home, and grid interactive efficient buildings can really help customers optimize their energy use and based on their particular preferences for heating and cooling and other energy services. So it really is a full spectrum opportunity across various perspectives. So I think there's, when you think about grid interactive efficient buildings and what they are, there's probably 4 key characteristics to keep in mind. The first one is efficient. This is the E in GABS. So it's about having buildings that have persistently lower energy use and have ultimately reduced demand on the grid resources and infrastructure. GABS are also connected. It might be achieved through two-way communication with either flexible technologies, communication with the grid, as well as communication with building occupants. They're smart buildings through analytics and controls algorithms that can co-optimize efficiency, flexibility, occupancy preferences, sort of multi-variable optimization. And then importantly, they're flexible loads. They can sort of serve as either resources to shed load or shift load into different time periods, both reducing the magnitude and the timing. And even on finer timescales, certain building loads can be used to modulate energy use and provide ancillary services. So this roadmap, as I mentioned before, is really intended to provide recommended key actions that could be taken by a wide range of industry stakeholders, and I'll get to those at the end of this slide deck. So first, we're going to estimate the value of the untapped opportunity to the power system that GABS presents. I'll talk a little bit about what GABS look like in terms of their technology features and important considerations for how these buildings are actually deployed in the field. We'll talk about these barriers to GEB deployment, and importantly, identify 14 recommendations to overcome those barriers. And again, this information is all available at gebroadmap.lbl.gov. One thing I also wanted to mention is that this document represents input from over 100 people in the industry, practitioners, researchers, regulators, policymakers. So really, I think it represents sort of a collective vision and covers the key areas for the industry. So the GEB opportunity. So this is the big headline. What are we talking about here? For the grid, it's really quite substantial. That GEBs could save up to $18 billion per year, or in totality between 2020 and 2040, we're talking about $100 to $200 billion in power system cost savings from deployment of grid interactive efficient buildings. You can see the values broken out depending on, they vary based on what levels of adoption you achieve in terms of the customers who adopt these types of technologies, how widespread that is, as well as sort of what's the grid scenario and what's the mix on the grid, whether it's low or high renewable energy. And capacity value is obviously a clear driver of this power system cost benefit. So you can see that that's quite substantial the higher the capacity value goes. On a purely kind of gigawatt and energy basis, so the peak demand reduction capability, current demand response resources are roughly on the order of about 10 gigawatts as a resource for the US, both residential and commercial programs. In our GEB potential study, we quantified, assuming either mid or high adoption levels, either almost tripling or more than quadrupling that value. In the high adoption by 2030, you could achieve a little bit over 43 gigawatts of peak demand reduction potential across the US with high adoption of grid interactive efficient buildings. So it's a pretty substantial increase over the existing amount. And this is roughly the same story on an energy basis, as you can see on this right-hand figure. When you look at both the demand flexibility and energy efficiency potential, you can almost triple existing energy savings from these types of programs by 2030 under our high adoption scenario. As a result of this analysis, the US DOE has set an ambitious but achievable target to triple the demand flexibility capability in buildings by 2030. So we're really shooting for these bars on the far right here that you can see. And it's not only a power system cost story and an energy and demand story, it's also an emission story. And you can see in our potential study here that we found about 6% of all power sector CO2 emissions, or 80 million tons annually by 2030, could be saved from grid interactive efficient buildings. This is equivalent to about 50 medium-sized coal plants, or about 17 million cars on the road gone as a result of GEBs. You can see here the regional opportunities vary depending on what the current grid mix, power system portfolio mix is, with the greater opportunities being in the upper Midwest and mid-Atlantic regions that are still fairly heavily reliant on coal power. So what is a GEB? So as we dive in a little bit more, we wanted to conceptualize what are the various kind of connection points and technologies that are at play, and what are the issues about integrating these technologies that need to be sort of further explored. So you can think about this in terms of layers within the building. When you start with just the physical systems, what's the hardware appliances within the building, then you have a layer in which there's sensing and actuation among those different physical systems. And then you have layers of control, whether that's local control for optimizing individual components of the system, or importantly, and I think is really critical for GEBs, is that supervisory control that spans multiple building services. Now, the user certainly interfaces at all of these levels. And then there's connection points outside the building, whether that is to additional distributed energy resources that might be co-located, storage, solar, PV, electric vehicles, as well as an interface with the grid, right? We talked about GEBs are characterized by being grid connected and interactive. So there is that bi-directional connection there. Obviously, integration is a key issue, both between the layers that are here, as well as across multiple end uses to really achieve a full building resource. Interoperability, standards, these are all critical things that need to be explored. We'll cover in the recommendations to make this happen. From a pure technology, like specific technology standpoint, I think there's some interesting examples of building technologies that could really improve and unlock a lot of the GAB potential here. We did a survey of some building technology experts and came up with sort of what are the highest DF enabled technology opportunities, both commercially available on the far left, as well as those that are in development. You know, depending on the layer, you can start with physical systems like heat pump water heaters and combination systems. Thermal energy storage is a very exciting opportunity in an emerging area for GABS that's in development. And then you have supervisory and control technologies, whether it's building automation systems, predictive controls, as an opportunity as well. So got to talk about barriers to maximizing GABS and getting widespread deployment. We created this value chain in which we talk about how GABS are developed, deployed, adopted, and utilized, and then the key stakeholders at each point in that value chain. And so you move from development and you have software and hardware developers and researchers that face issues around sort of lack of technology development or lack of standardization and interoperability. Deployment, which really faces installers, aggregators, or ESCOs and utilities around maybe underrepresenting EE and DF and utility planning, limited financial opportunities or sort of business model barriers there for aggregators. The adoption of GABS is key for consumers and building owners and managers as well. They may have insufficient or sort of a lack of awareness of the value proposition. And some of this technology, frankly, is quite complex and can be pretty expensive in terms of that initial capital outlay. And then the utilization of this resource, you know, utilities as well as grid operators, wholesale markets may not trust demand flexibility performance or view it as a risky resource. They may just not have a financial incentive. And then supporting this value chain are regulators, policymakers, researchers, and advocacy groups regulating, supporting, and facilitating the GAB value chain. And then they themselves face barriers related to lack of information to develop these supporting policies, lack of champions, as well as, you know, maybe a status quo bias. So in order to overcome these barriers and achieve the potential that I described, we laid out 14 recommendations that we organized across 4 pillars. That I've tried to summarize these in terms of, like, you know, what is the recommendation under that pillar, and then what's an example action. There's a lot more to this. I have some appended slides. If there's a particular pillar you'd like to dive into during the discussion, let me know and we can get into some more detail. But at a somewhat high level, the first pillar is about advancing GABS through research and deployment and development. This is really sort of a traditional R&D type set of recommendations. So both developing, researching, and accelerating the deployment of those technologies, especially the exciting ones like thermal energy storage that I had talked about. Accelerating interoperability to really optimize performance. So that might be accelerating the adoption of existing open standards or potentially developing new standards. And then collecting and providing data and developing methods to both benchmark and evaluate demand flexibility performance. So maybe expanding currently existing energy efficiency data set and benchmarking tools as a place to start. The second pillar is about enhancing the value of GABS to consumers and utilities. I think there's some in here that may be of particular interest to some of the ESIG members. This might just be simply improving and expanding the types of program offerings. So taking energy efficiency programs and the success we've had there and incorporating demand flexibility components and marketing those with a focus on what the consumer wants. Expanding consumer knowledge and consideration of price-based programs. So how do we go from pilots to full-scale deployment of some of these more novel pricing options for customers? Introducing incentives for utilities to deploy demand flexibility resources. So are there things that we've learned from revenue decoupling or performance-based rate making that we could apply to encourage investment in GAB resources? And then I think what's also important is comprehensively incorporating demand flexibility into utility resource planning. You know, ensuring that we have a comprehensive package of measures that are considered in the analysis, accounting for all their value streams, whether it's integrated resource planning or distributed distribution system planning. The third pillar of recommendations is around empowering GAB users and operations. So it's a very sort of customer focused piece. So understanding how they interact with GABS and the role of technology, developing tools to support the decision-making process. As I mentioned, these technologies can be rather complex. And so providing tools that allow them to think about how to incorporate demand flexibility into their retrofit or new construction projects. And then really importantly, we got to develop a workforce, right? So can we leverage existing workforce programs to integrate advanced building technology and operations education and training? And that might be accomplished through establishing building training and assessment centers. And the fourth pillar, this is really geared towards state and federal decision makers. So how do we support GAB deployment through specific enabling programs and policies at the state and federal level? Maybe it's lead by example. You know, the GSA program has their own GAB roadmap, and they have, you know, participation in demand response and energy efficiency programs. It might be expanding our funding and financing options for GAB technologies, or even expanding codes and standards to incorporate demand flexibility. And then finally, some states are considering demand flexibility as an explicit state target or a mandate, or maybe building a decarbonization goal. For example, like what Obadiah and SMUD have done, that may drive more demand flexibility as a resource to meet those decarbonization targets. So with that, I will stop. That's what I had to present. I think we'll have time for Q&A, so I'll pass things back over to Obadiah.
Great. Thank you very much, Andy. That was a really helpful overview and really speaks to the potential that's out there for this kind of flexibility from the building sector. Our next speaker is going to be Mark Frankel. Mark is the Director of Research and Innovation at Ecotope in Seattle. Mark's been consulting on energy efficiency and sustainable design for over 30 years and has consulted on hundreds of capital projects and portfolio strategies across North America. He's been engaged in research and policy development focused on leading edge building design outcomes that magnify and proliferate best practices in building performance. Mark has served on the boards of the USGBC, ILFI, Cascadia Green Building Council, and the Seattle 2030 District. Mark's a lead fellow, a member of AIA and ASHRAE, and a licensed architect. So welcome, Mark, and he's going to be speaking about planning grid flexibility into buildings.
Thanks very much, Obadiah. It's nice to be here virtually. I'm sorry I'm not in the room with you guys. I love standing in front of people and talking to them and looking in their faces. So you guys will just have to pretend I'm there and work with me. I'm going to talk about two separate topics. Generally, my career has included two long stints at two firms. One of them is Ecotope and one of them is New Buildings Institute. I'm back at Ecotope for my second stint, for my second decade of Ecotope time. But I left New Buildings Institute only 2 years ago, where I was the technical director and was responsible for kicking off the Grid Optimal program. So I'm going to talk about that too first. So just briefly, Ecotope is a design, engineering, and research firm in the Seattle area. We've been in business since 1975. We're very focused on leading edge design strategies and research. Our mantra, if you will, is to electrify buildings. Design for off, which is our interpretation of deep efficiency. A number of our buildings spend 30% or more of the year with no systems running in passive mode. And that's the most efficient way to run an HVAC system, is to turn it off. And then when matters, the recognition that we can't think about annual energy efficiency anymore. We really need to think about time of use and when you're using energy as the goal as we try to decarbonize buildings and the grid. So with that, I'm going to pivot to Grid Optimal, and I really appreciate New Buildings Institute loaning me some of their slides to talk about this. This is something I worked on with Obadiah from starting in 2018, and this has sort of come to nice fruition with a lot of interesting resources that I'm going to talk about very briefly. The purpose of the Grid Optimal initiative is to start sort of thinking about how we incorporate grid integration into the building sector. So we started with a bunch of metrics to think about, how are we going to sort of measure what grid integration looks like, and can we give the design community something they can use to decide the performance of their buildings in this context. We were working right from the get-go with the USGBC, and this program got incorporated into the LEAD program. As pilot credits, it's worth 2 or 3 points as you address it. And there's specific guidelines for how to address grid integration as part of LEAD, which I think is a really great vehicle for expanding this into sort of program efforts. It includes design and operations guidance to help designers understand what it means to build flexibility into buildings, and building operators understand how to deploy that flexibility, which is also a really critical part, of course, of successful grid integration. There's a component of utility program guidance to help start to sort of a quick start guide for developing utility programs around grid integration. There's also been efforts on code and policy development. I've recently been involved in incorporating load flexibility requirements into proposals for the IECC, ASHRAE, and the Washington State Energy Code. So this is just a foot in the water on grid integration into code, but it's an important start. And then NBI has done a really nice job making this data available for researchers and others to understand better and look at. I'll show that briefly. So, oops, jump to. So these are the core research metrics that Grid Optimal started with to try and figure out, can we figure out what the measurement of this is and what's good versus bad versus indifferent in here. And these are the criteria that were used in thinking about this. You'll understand all these. I know all you guys in the room are pretty familiar with this terminology, but obviously the peak, how well does the building peak align or disalign with grid peak? If it's got renewables deployed, are they using them on site first? That's a priority for utilities, so they don't have to act as the battery for everybody. So self-utilization or on-site renewable utilization efficiency, really good metric. Carbon is an important metric, becoming more important in some regions, of course, so that's one of them. Efficiency versus baseline, we definitely recognize that energy efficiency is part of grid integration, and I'll talk more about that a little bit later. And then the length of time that you can offer flexibility to the grid, whether it's short-term, say an hour, or long-term, 4 hours, whether it's dispatchable, and the degree to which it includes resiliency metrics. So those are sort of the high-level metrics that went into the Grid Optimal program. And I should mention also that this program was sponsored by a bunch of utilities, including SMUD, which, as I mentioned, is how I sort of got in touch with Obadiah on this topic. But it's been continuing support from utilities through the life of the program, which great collaboration. I mentioned that this is incorporated into the LEED credits. There's various different ways to achieve LEED credits. Just paying attention gets you partway down the road where you're actually putting these metrics into place in your design, which is a really important first step for the design community because this is really new stuff for them. And then succeeding at the metrics is, the next tier, if you will. And there's different ways to use this, recognizing that the grid is different in different parts of the country. You don't have to do every metric, but you can choose the ones that you think are most important to you and sort of focus and succeed deeply in certain categories. So there's different ways to use this in LEED. And maybe that's a model for utility programs around the country as well. NBI has done a nice job of putting together calculators that you can put your data into and look at generating some of the metrics that it requires. That, again, education is a really important component of this. The design community is not familiar for the most part with these ideas, and part of the campaign, if you will, to get grid integrated buildings to be more widely adopted is helping the design community understand what exactly we're talking about. So there's a lot of sort of help here, if you will, for deployment. I mentioned that NBI has put out some very nice glossy virtual guides on by building type, by region, and also supporting operations, which is a critical part of this. So all these resources are available at the New Buildings website. I encourage you to go there and grab some of this stuff. It's a really great resource. And I mentioned that there's sort of a quick start guide for utility programs, and this is also published as well as guidance on code strategies. So, I'm very fond of NBI. I spent 15 years there, and they do some great work, and there's some really good resources there. So I encourage all of you to find this stuff. It's very easy to do. The last piece I want to talk about, which is a nice way for me to transition to the Ecotope work, is this Grid Optimal Measure Impact Analysis tool. I'm sure many of you have seen online tools that you can manipulate. This is Tableau, and you can sort of put in your own parameters, and the data changes before your very eyes like magic. It's really cool. But this particular screen and every one of these tabs across the top here is a different way to look at the data from a bunch of analysis that NBI did. Some of the national labs provided data on building energy use and load shapes, and it's all sort of aggregated and digested in this tool, which is great. But here's a key part that I want to talk about next, which is coincident peak reduction from efficiency measures. When we talk about programs and making grid integration a program. I think we really need to leverage existing incentive programs very effectively so that we add to those and recognize the value of efficiency in grid integration and add to that rather than start fresh with a whole new approach. That's my own opinion. I'm probably not the only one that thinks that, but maybe not everyone agrees. So let me transition to Ecotope a little more and bring this all back to grid because we're doing some really interesting stuff on this as well that I'm going to share with you. I mentioned that Ecotope does design and research. For the last decade, we've been really deeply involved in trying to help transition the market to the use of central heat pump water heater systems. So not the residential unitary stuff that you see in houses, but big central systems that serve multifamily or other big projects. Our expertise happens to be multifamily at Ecotope. We've got over 75 systems designed and deployed, and another at least 10 on the books right now on the boards. We work directly with manufacturers to come up with system configurations and evaluations. We've worked to package these systems onto skids that can be delivered on a truck and dropped on the roof so that it's not custom design every time, but also to generate packages that can be spec'd as groups or whatever, just trying to break through the barriers of uncertainty and unfamiliarity with this system to make it easier to deploy. We've also worked on building performance specifications and standards. The advanced water heating spec that we worked with NEA on is becoming an industry standard. We're working currently with a number of utilities on program development about central heat pump water heaters. We've also built sizing tools and modeling analysis tools, which are also incorporated in the Title 24 requirements. Our sizing tool, the EcoSizer, actually includes a load shift feature. You can sort of define a time period that you want to have load shift and how much of the time you want to be guaranteed that you're going to get the load shift in those 4 hours, say. And by manipulating these sliders, it will scale the capacity of the storage tank and the size of the heat pump to achieve that time period of load shift. So, and that tool's out, available. A number of utilities refer to it directly and manufacturers use it as well. We do a lot of testing and monitoring, so we have good data on load shapes from our own projects and from other projects we monitor. I mentioned we've done some codes and policy work on this. Central heat pump water heaters are pretty much required now in the city of Seattle for multifamily. It's really hard not to put them in. And we're working on design guidance and system performance research. So sorry, but I just want to give you a perspective on the different angles on this that we're coming from, because I think that'll help sort of recognize how well integrated load shift can be in this. So for those of you who are not familiar with this technology in multifamily, this is data from Seattle. In Seattle, 80% of our multifamily buildings in the Pacific Northwest existing are use electricity as a fuel for hot water. So 80%, that's really big. Nationally, it's about 50% and 50% gas. A lot of those electric are in-unit electric, small tanks. Those are really hard to replace with central heat pump water heaters. But most of the new stuff is going to central. So if you look, we've done a number of retrofits of electric boilers. And the savings when you convert an electric boiler to an electric heat pump system is about 17% of the total building energy use. And I really can't think of another technology where you can deploy one technology in a building to get 17% savings. I mean, there's additive savings from envelope and performance upgrade, but that is a huge chunk of energy. And when you look at domestic hot water energy use in the commercial sector, this is from an analysis of PNNL end use data and CBAC's population data and so on and so forth. And basically our analysis suggests that in the US, nearly a third of all domestic hot water energy use is used by the multifamily sector. The next big three are food service, grocery, and lodging. And together they account for more than 3/4 of all domestic hot water energy use in the commercial sector. So utility people I know kind of get really excited when you can focus a program on a single sector and have a big impact, because it's so much easier to write rules and guidelines around single sector than it is around, that has to work for all project types. So to me, this is a really huge opportunity. So I mentioned that we've done a lot of work on load shapes, and this is from data from a project in Seattle. On the left, this is what a typical multifamily market rate housing load shape looks like. There's a big morning peak and a secondary afternoon evening peak. And there's a lot of variability by day. Weekends are a little flatter. But this 2-peak load shape, I know all the utility people in the room, which I think is probably most of you, are probably looking at this going, there's a big opportunity there, because those are the time periods we really need to address. And I showed you the variability of this between the peak day and the average day. So the red line in this graph is the peak sizing criteria that we use to size the systems for these buildings. And the green line is the average load that these systems have to meet. So as you're probably aware, central heat pump water heater systems rely on a very large storage tank relative to the engine. In a gas boiler, you size the engine to meet the peak load, and the storage is to meet the little loads in between, so the big engine doesn't have to crank up all the time. It's pretty much the opposite in central heat pump water heater systems. You size for large storage tank, and the engine is just to replenish the water over time. So we have this, we're sizing for this peak load. We have all this storage available in these two periods of the day, most of the time, just with standard design, no special criteria of oversizing. You have this spread. So now let's look at how this plays out in a whole building energy use. So this graph is total building energy use for multifamily building in January, morning peak and afternoon peak with electric baseline, right? So electric baseline, I know it makes my story a little better if I use electric baseline, but it's not unheard of. 80% of multifamily in the Northwest use electric hot water baseline. So if we deploy the central heat pump water heater system on this building, this is the difference in peak load between the electric hot water baseline and the central heat pump water heater system. So all the things you're seeing here is blue is efficiency savings, and all the difference in vertical is peak savings, right? So now the next graph I'm going to show you is just hot water, same thing, but it's just the hot water load itself. So this blue is the hot water load in the base case. The gray is the normal operating characteristics of the heat pump water heater system. And I'll talk about the yellow line in a minute. But if you look at this, so again, the blue, this is all the efficiency of the system. And the difference in the height between the gray and the blue is the peak savings. So the way I think about this, I know we talk about GABS as having all these features of smart and integrated and dispatchable and everything. But to me, this is like the base load in your grid system. You know, if you've got a nuclear plant on your grid, you run it all the time. You never turn it off. You don't turn it off because power is low. You don't crank it up only when you're peaking. This is the base load, right? It just runs. And that's the way I think we need to think about efficiency in the context of load shape, right? Because it's just there. It's always there. It's always serving you, whether you need extra that day or not. You've still reduced the peak capacity just based on deploying the system. So in this particular graph, the city of Seattle has a pilot time of use rate that targets the hours between 5 and 9 p.m. And they want you to not use energy in that time. So this yellow line shows the operation of this heat pump. If we oversize the tanks enough to always meet that peak period. And so when the heat pump would have come on here as the afternoon peak starts rising on the building, instead it's held off until the end of the period, and then it comes up and runs. And you can see on the other side of the graph, it runs more hours into the wee morning to make up the difference. And unsurprisingly, this trapezoid of gray that we've cut out of that during the peak period is now replaced with a trapezoid here in the middle of the night, which is what we want in this scenario. So the thing about this is that if we talk about the incentives to achieve this in the heat pump, if we were going to incentivize a transition from electric baseline to central heat pump, you know, we get about half of this peak load savings with the incentives on efficiency. The second increment of savings on peak is just from oversizing the storage tank. So if the cost of this, you know, is the cost of getting this blue savings peak reduction is 95% of the cost, and that's what we do all our calculations on energy efficiency on. And the cost of getting the second half of the peak load savings is about 3% more to oversize the storage tanks on a system you've already paid for. So if we can make that linkage between efficiency incentives and peak load incentives, there's a lot to work with here, both in increasing the incentives for efficiency, but also expanding the capability of that building to deliver efficiency in this context. So two more quick slides. One, when we talk about the features affecting grid response in central heat pump water heater systems, there's the capacity of the heat pump. That is, how fast can it recover? There's the storage capacity, which is the main thing that's the only thing I manipulated in the previous slide, is the storage capacity. And that's the easiest one to manipulate if you've got a little bit of extra space. You could conceivably run these systems at a higher water temperature in the storage system and mix it down for the distribution. That is challenging depending on what refrigerant you're using to power your system. CO2 systems, which we are very fond of nowadays, can elevate the temperature somewhat, but it's not as easy as just increasing storage if you're trying to get through a load shift, right? Temperature can be more useful in a dispatch where you want to shift or shed or whatever, but if you're just trying to run through a peak period, storage is probably the easiest way to do it. Of course, there's control implications. In Washington, Oregon, and California, this equipment is required to have a CTA 2045 port or an eco port, which is basically a ready-made receiver for utility equipment that sends a signal and tells the hot water heater to shift or shed or shimmy or whatever controls are being dispatched. So that's sort of on board already for this equipment. There's some supply chain issues in Washington with the start of deployment, but it's coming. Finally, I will just say that there's a lot of discussion when we talk about decarbonization. Are we moving gas load onto the grid and therefore adding more challenge to the grid? And we've done some work on this, looking at the national data on these sectors. Again, this is multifamily, food service, lodging, and grocery. Here they are all together, those four sectors. The split between electric, which is the green, and gas, which is the gray, looks like this right now. And if we convert everything to heat pump water heater, even though we've gotten rid of all this gas, we still end up with a lower electric load than current. So the savings are so substantial in moving to central heat pump water heaters that we actually don't necessarily add load to the grid in making that transition. And that is the end of my presentation. Thank you very much.
Well, thank you very much, Mark. Appreciate the presentation. A lot of good stuff in there. And now we have saved the best for last. We've got Henrik Madsen joining us all the way from Denmark. Sorry for the late hour there, Henrik, but he has assured me that he has dosed himself with some extra coffee. So hopefully he can bring that energy for us. So just a little bio for Henrik. Since 1999, he's been a professor in stochastic dynamical systems at the Technical University of Denmark. He's got several awards. In June of 2016, he was appointed Knight of the Order of Dannebrog by Her Majesty the Queen of Denmark. He has authored or co-authored approximately 600 papers and 12 books. Currently, he is the most cited researcher worldwide related to demand response and smart grids. So pleasure to have you here with us today, Henrik, and take it away.
Thanks a lot, and it's a pity that I couldn't be there. That would really have been nice. So, but thanks for the invitation. So what I will show is how we can use digitalization and a smart energy operating system together with a flexibility function to unlock the flexibility in buildings. The exact same procedure can be used to unlock flexibility in wastewater treatment plants, in supermarket cooling, electrolysis, power to X facilities, district heating, and so on. Of course, some of the challenges we are facing is the transition of the power system or the energy system, because we are moving away from a system where we had large power plants with a lot of intelligence and optimization and so on, to the new system where we got rid of these central power plants. So that means in order to balance the power system, we need to move the intelligence to the end user sites where we have the building, we have industries, we have supermarket, wastewater, and so on. But of course, in this talk, I will focus on buildings. And I come from applied mathematics and computer science, so I'll focus a lot on how we do it by use of data and use of digitalization. One thing I would also stress is that we need some disruption in our thinking. First of all, we normally, when you talk about markets, you bid into the markets with a quantity, a volume at some price and so on, and then you have a demand supply curve, as I guess you all know. And then you have the cross, the intersection where you have the clearing. And of course, in mathematics, where I come from, this is what I would call a static, deterministic and linear problem, because you simply stack the bit also. So, but most importantly, it's a static problem. And if a building or maybe a supermarket has been flexible for half an hour, maybe it cannot be flexible for the next half hour. So we need to go away and rethink this. This problem has to be converted from a static problem to a dynamic problem or description. And that's where we are using the so-called flexibility function. I will not go into all the details here, but one thing I will also emphasize is what we are providing with our smart energy operating system is one solution which can actually solve all the grid, all the services need for the grid, voltage service, congestion managing, and things like that. But I'll come back to that, of course. So in order to do that, it's clear when you look at the end user side, it's rather complicated, and that means we need models which can learn from data. And in order to do that, we have developed the concept of Greybox modeling, which are models of a building, of a supermarket or whatever, which are highly simplified buildings, but they are optimized in two ways. They are simple, so they can be used in real time. We can predict what will happen in 2 minutes and 5 minutes because the models are very simple. But most importantly, the models are optimized for assimilating information from sensors in real time, so they can learn from data in real time and use this in the control and the setup. So these Greybox models, and sometimes we also call it data-driven digital twins, are important elements. Another thing is, which is important, is that we need to have models which are coherent on all scales. So we need to have a system, and that's what we call the smart energy operating system, which can operate from the appliances to the building, to the district, to the city, to the country, to the continent, and do it in a way which are coherent across the different scales. And this is what we have achieved with our smart energy operating system, where we up here we do have conventional market bidding, because that's the day ahead markets and so on. So that's where we set the price level, I would say. But what I'll focus on today is the lower level here. And the lower level here, we have the buildings and wastewater treatment plant, for instance. And above this, we have the distributions, the power distribution system operator, the DSO. And maybe we have some balance responsible party or a local aggregator. And the most important thing is that here the dynamical aspects of the assets are important. And these are the key to link the markets to the dynamics or the physics. And what we do from some level here is we simply broadcast the price to the end user. So in real time, we only broadcast the price. So it's a one-way communication system in real time. But then we learn the flexibility functions based on data, and these flexibility functions are used by the players to in their controllers, and I'll come back to how this is done. So the flexibility function is linking the markets to the physics. The classical static markets with the low-level local flexibility markets. And we do that by a hierarchy of controllers. And I'll show some examples later on related to building, where I'll consider this level 3 and level 4, the two lowest level in this smart energy operating system. So just to show example of controllers at these two lower levels, if we have a setting where an operator would like to do peak shaving, then of course, and we have some consumers which are react to prices, then of course there is a relationship between the price and the load in these buildings or clusters of buildings, and this is very often complicated. So here I don't specify a model, but there is a relationship between the price and the load. This reference signal can also be the voltage. So, and if we can manipulate the load, we can also manipulate the voltage. And this is also complicated, but by using machine learning and a lot of data, we can of course estimate this function, and then we can find the price which minimizes the offset from what we want. So that's a reference-based type of controller. And this price, which is a result of this controller here, is then sent to all the buildings. And some of the buildings could, or some of the end users could also be a wastewater treatment plant or supermarket, but of course here we'll focus on buildings. And then the price is used at the building level in something which is typically an economic MPC control, where we simply minimize the cost. And a typical building model for this type of control is such a linear model like this. So here we have a model, could be a Greybox model also. So these shows how these two levels of controllers are nested or linked. So now I'll show some examples on the controllers. One on level 3, where we assume that someone would like to do some peak shaving by sending a price signal to a cluster of buildings. And here we see aggregation over 20 buildings, where the price here goes up. I hope you can see my cursor. And when the price goes up, the load goes down. And when the price goes down, the load goes up. So the problem here is boiled down to a problem in my basic course on time series analysis by finding a model which relates the price signal to this load signal. And that's can be done by a Greybox model or an Armax model and so on. And this is I'll come back to this type of models. But what we can see, and these are analyzing some of the old, very well-known data from the Olympic Peninsula project, where when we have exposed these buildings to a step change in price, then the load went down to with this amount for about 5 hours, and there's also a little rebound effect. In Denmark, and what we see, and in particular, we are using a lot of district heating, and then we have a flexibility which can be 30, we can reduce the load with 30 to 40% and up to maybe several days, because there is a lot of water and flexibility in district heating systems. So what I mentioned before is that if we have a relationship between the price and aggregated consumption, then we have estimated this model. And if I have this model, then I can also use this model in generating the price, so I get the voltage or load I want. So that's pretty simple. So estimating this model is one of the first exercises in my course on time series analysis. And if you have a dynamic model here, then finding the controller which are able to control the price or get the price so we can control the voltage is one of the basic exercises in our courses in control theory. So this shows just how we can achieve peak shaving in a specific example by this approach. So the setup here is a generic setup, which is also used in Annex 82, and I know Andy is an important member of this, is the so-called flexibility function, which explains how the price relates to the response. The penalty can be the price. It's very often the price, but it can also be emission or CO2 or whatever. So we can, and I'll come back to some examples where we minimize the CO2 emission. And the controller, the reference-based controller, can be designed so we can get voltage control, we can get congestion management and balancing and so on. So if we then go to the lower level, the building, and this is actually a very particular special building, that's a summer house with swimming pools. And what we do is simply we're using we are overheating the pool when we have, or we're using the flexibility of the pool to create a lot of flexibility for the grid. So this shows how the share of CO2 in the electricity in Denmark varies around the 1st of December 2016, so that's 6 years ago. And of course, in December, we don't have much sun in Denmark. It's pretty dark, but we can have a lot of wind. Sometimes 70% of our electricity at that time was from wind. Yeah, it can actually be more than 100. And sometimes we don't have much wind. So of course, the simple idea is to heat up the pool when we have a lot of wind, and don't heat the pool when we don't have wind. So this is something we implemented in the buildings with a smart house controller, where we send data from the building to the cloud, and then we get the weather forecast, and we send then the control signal back to the control the temperature and the flow in the houses. So this shows one house with price-based control. We are here now, and this is the prediction of the prices for the next 24 hours. And the controllers then decide to heat up the house when the prices are minimum. And this blue line shows the band where the temperature in the pool should be within this band. This house is another house which has decided to focus on a CO2-based control. So instead of minimizing the cost, they minimize the CO2 footprint of the house. So, but the setup is exactly the same. The only difference is this is a forecast of the CO2 footprint of the electricity mix reaching that house for the next 24 hours. And here we can see the minimum CO2 is around these hours. So the controller decide to heat up the pool extra in these hours, and then we don't need to heat it for maybe more than a day. So this is built into a national center. Now it's also acting as a European center for smart energy system, where we have built up or are building up a control room and data spaces for providing these grid services, using the flexibility not only in buildings but also wastewater systems and supermarkets and electrolyzers and so on. So, and as also indicated or emphasized by the other speakers, buildings has a lot of flexibility potentials. So the future weather-driven energy system driven by wind and solar really calls for a digitalization of the energy systems and for unlocking the flexibility in buildings and of course in the entire city. And in my view, that calls for a deep digitalization of the grids and the energy system. So we need also sector coupling, and we need to digitalize all the energy sector. And we have proven in many cases, and we are using it daily now also, that buildings can really provide a lot of flexibility for the grid, for peak shaving, for one example we are working on now is to control the temperature in transformators, so we can really control the load so we don't overheat the transformators in DSO areas. And we have built this data hub for providing the flexibility services for a lot of players, like not only buildings, but also, for instance, wastewater treatment plants. So thanks a lot for your attention.